Wanted to work through an example of the photoelectric effect. The photoelectric effect is the emission of electrons from a material, generally a metal, by illumination with light, generally ultraviolet light. It's the classic example, a classic example of light acting as particles. Quanta, discrete units of light that carry energy, that carry momentum. In the photoelectric effect, we imagine that these particles of light, these grains of light, are colliding, striking the electrons in the metal, and then knocking out the electrons from the metal into the surrounding space. In this particular problem, we're asked to consider three different metals as targets. There's lithium, there's beryllium, and there's mercury, all metals. And we're told that their work functions are respectively 2.9 electron volts, 4.98 electron volts, and 4.5 electron volts. We're then told that we illuminate these metals with light that has a wavelength of 390 nanometers. Now, you probably remember that visible light has a wavelength from 400 to 700 nanometers. 400 is the blue end, 700 is the red end. This 390 nanometers is right at the blue end of the visible region. So it's right on the edge between visible light and ultraviolet light. And so we're going to first ask the question, well, with this color light, this 390 nanometer light, is it possible that the light can emit photoelectrons, photoelectric effect electrons from lithium, beryllium, mercury? And then if it is possible to emit photoelectrons from those materials, then we're going to calculate the maximum kinetic energy of the electrons that are liberated from those materials. To solve this problem, the first thing I want to do, the first thing I want to calculate is the energy of photons that correspond to 390 nanometers. Again, thinking about light as photons, stream of photons, is the key to the photoelectric effect. We want to know the energy of the photons corresponding to this light of 390 nanometers. So here's the relation I'm going to use to determine the energy of the photons from the wavelength of the light. So this is a combination of two important equations. One is the relationship between the energy of the photons and the frequency of the light. This is Planck's famous equation, where h is Planck's constant. And then the second relationship I used is the relationship between frequency, wavelength, and speed of light. The speed of light is the product of the frequency and the wavelength. I've rearranged that to replace frequency here on the left by c over lambda, speed over wavelength on the right. I've now got an expression for the energy of the photons in terms of the wavelength of the photons, the quantity that I know, and constants of nature, Planck's constant and the speed of light. And so I can just plug in all these values and calculate the energy of the photons. I'll go ahead and do that. And so here's my calculation. Here is Planck's constant, 4.15 times 10 to the minus 15 eV seconds, energy times time. I've used Planck's constant in units of eV seconds rather joules than joule seconds because it's much handier here when talking about photon energies. I plugged in the speed of light in meters per second. It's 300 million meters per second. And I plugged in the wavelength of the light. It's 3.9 times 10 to the minus 7 meters. You can see here that when I carry out this computation, the units of meters in the numerator here, denominator here will cancel out. The units of seconds in the numerator here and denominator here will cancel out. I'm just going to be left with the units of EV. And it comes out to be after multiplying and dividing by these various numbers, 3.18 electron volts. That's the energy of 390 nanometer light. That's the energy, the photons, the little packets of light, for 390 nanometer light. Well, to determine if this light of this wavelength and this energy packets can emit photoelectrons from lithium, beryllium, mercury, all we got to do is compare the energy of the photons of light with the work functions, which is an energy of the different materials. If the photons have an energy that is greater than the work functions of the material, that means that we can lift those electrons out of the metal. If the photons have an energy less than the work functions of the material, then those photons can't lift the electrons out of the material. So making this comparison, lithium has a work function that is 2.9 electron volts. The photons are about 3.2 electron volts. So the photon energies are greater than the work function energy. And so the photoelectric effect can occur. I've indicated it with the check mark on lithium. On the other hand, beryllium has a work function that is 4.98 electron volts. The photons are only 3.2 electron volts, so they're insufficient to liberate electrons from beryllium because the work function of beryllium is larger than the photon energy. And so I indicated that photoelectric effect is impossible with this frequency, wavelength, energy of light on beryllium. And similarly for mercury. Mercury has a work function that's 4.5 electron volts. That too is bigger than the photon energy, 3.2 electron volts. So the work function phi is bigger than the photon energy E. So for mercury, you also can't have photo emission of electrons with that color, wavelength, frequency, energy of light. So we've discovered here by just comparing the energies of the photons and the work functions of the material that only lithium can undergo the photoelectric effect for this wavelength of light. We can also calculate then for lithium what the maximum kinetic energy of the electrons will be. The maximum kinetic energy is just the energy that's left after absorbing the photon, using some of its energy to release the electron. There'll be some left for lithium, and that some left for lithium is the maximum kinetic energy that the electrons, liberated electrons, can have. So as an equation, that's the energy that's brought in by the photon, less the energy that's consumed to liberate the electrons. That's the work function. So this is going to be 3.18 electron volts minus the 2.90 electron volts. And what remains is just 0.28 electron volts. That's the maximum energy of the electrons liberated from the lithium. There are no electrons liberated from beryllium. There's no electrons are liberated from mercury, so there's no maximum kinetic energies here. It's not relevant because the process can't occur. Anyway, that was an example of photoelectric effect. Photoelectric effect was a crucial effect, a key effect in uncovering the particle nature of light, the sort of granularity of light, fact that light at quantum level comes in little packets, in little quanta, in little units, and that those units have energies and momenta which are normally particle-like properties that are related to the wavelengths and the frequencies of the light.